Okay, so basically today we cover example of the fundamental theorem of calculus for line integral. The acronym is fundamental theorem of calculus, pero of specific for a line integral. Let me recall quickly what is that. So suppose we have one line integral of the one vector field that they are, suppose circulation, no flux. Well, this is equivalent to say que this, suppose que this vector function come from the computation for the gradient of the one potential function that they are, is because this vector field, this one, is conservative. And since it's conservative, we can compute the line integral using the potential function. When you evaluate, no integral anymore. You evaluate the potential function and the endpoint minus start point. It's very, very similar to the fundamental theorem of calculus that you see in Cal 1. Let's see example. Example 1. This is easy. In my opinion, it's super easy. And suppose let's do one problem in 2D and one problem in 3D. So for example, I have the vector field is given is 4x squared plus axy, comma 3y squared plus 4x squared. So this is given. And what do you want? Well, you want to compute the line integral and this vector field dr. It's a dot product, remember, dr. And one curve, but this curve, for example, is represented by a curve. Entonces this point, this is 0,000, so 0,0 is the 1 point, and 1,1. And the trajectory is, I don't know, completely crazy like that, right? In this direction. So when you see this kind of problem, okay, no specification, the equation for the curve C, this is the curve C, it's because this sound like a conservative. Entonces, si es conservative, remember, I don't care, it's path independent. I need only the information I need is the 2 point, no? The start point, the starting point, and the ending point. Okay. So first of all, I need to prove somehow that this vector field is conservative. The fantastic way to prove this is using the curve. You compute the curve of this vector field. If the answer is 0, then the conclusion is conservative. Okay, the formula for the curve in 2 dimensions is qx minus py. Easy. Entonces, the q, remember, this is p expression, and this is q expression. Derivative q with respect to x. So I focus this. If you differentiate with respect to x, this is 8x minus something. And you differentiate this with respect to y, well, this is 0, it's done depending of y, and this is ax. Okay, good, that's 0. So the conclusion is yes, it is conservative. vector field. Ajá, entonces now, in order to find, entonces the conclusion is conservative is because this vector field comes from the potential function. Entonces the way to find the potential function is using the anti-gradient. Anti-gradient, you take, you take the integral, the antiderivative p dx. Okay, because you suppose, what the idea? The idea is, actually, this is come from for the gradient. This is partial derivative f with respect to x. And how you remove the partial derivative, antiderivative with respect to this, and it come from for the one f, little f represent the potential function. Okay, don't worry. So I copy, just copy. The derivative b, who's b? 4x squared plus axy, derivative with respect to x. And you consider that the y is a constant. Entonces es, well, this is qb, entonces 4/3 x qb, because you're increasing power rule of the derivative, plus a, entonces x is x squared over 2, and y stays the same, plus something. Oh, leave it like that. Plus something means, I want to illustrate this idea, but not necessary. You have another function, g, I want to call it, depending of the variable that you don't find the antiderivative. You antiderivative with respect to x is because when you differentiate backward, this guy is 0 because you differentiate with respect to x. Little bit simplification. This is 4/3 x to the cubic power plus 4 x squared y plus another completely arbitrary function depending only of the y. Okay, no problem, I understand. Now that's it, no, because it's 2 dimension. So I need to compute the anti-gradient, dimension by dimension, q dy. So what is the expression for the q? Well, the expression for the q is 3 y squared plus 4 x squared y dy. Entonces 3 is a constant, I put outside, and you apply the power rule, it's y cubed over 3. Oh, by the way, this 3 is cancelled, why not? Plus 4 x squared is a constant, and this is y squared. Wait, why? Sorry, let me make a mistake. Where? Wait. Sorry, mistake, no? Mistake. The mistake is that my expression do not contain y here. Entonces es, when you apply the antiderivative with respect to y, is y cubed plus something, plus, okay, antiderivative this is a constant, no? Entonces 4 es 4 x squared y, no? Plus, well, another arbitrary function depending only of the x. Super. Okay, let me simplification. This is 4/3 y cubed, plus 4x squared y plus h of x. Entonces now, in order to determine what is the original potential function, wait, relax. I'm crazy today. Okay, this is 1, no? This is 1. This is 1. 3 cancel out, y cubed. Let me check it out. Okay, super. Okay, super. Now, what is the potential function? Well, the potential function is super easy. It's the collection. Any element you compute before. Okay, so now you take this 4/3 x cubed plus something. You see, wow, this and this is exactly the same. I take it. or x squared y. Pero take it one time, no repetition. Okay? Now, to say what about the rest? Well, I saw here y cubic, que I suppose que this function is this function. This is the justification. And plus, you put plus y cubic. And also similar idea happening here, right? This h of x is this. Pero es easy, no necessary identification. You take the collection. So the monomial expression is non-repeated, you take it. And the monomial expression is repeated, you take one time. And this is my potential function. So what should I do? Well, evaluate. Evaluate in between 1 and 0, 1, 1. So you, in order to find the line integral, you evaluate f and 1, 1 minus f and 0, 0. Bueno, en 0, 0 es obvio que es 0. En 1, 1 es 4/3 plus 4 plus 1. Entonces, the answer is 4/3 plus 4 plus 1 is 19 over 3. Super easy. Super easy. Let me summarize the idea. The idea is clear. First of all, in step 1, you need to prove that the vector field is conservative. How you prove that? Find the curve. If the curve is 0, yes, just we keep going in this direction. You find the anti-gradient here. In 3 dimensions, well, 3 dimensions is more complicated. You integrate 3 components, but in this case, no, it's 2 dimensions, you integrate 2 components. Now you get, the most important moment is the moment that you get the potential function. Look. And you evaluate in this endpoint minus start point. And you compute the work done, or, well, no, it's the circulation integral in general, mathematically. See, physically, and this vector field represents force. Of course, I understand that the meaning of this circulation integral, line integral, is a word. Not necessarily always is a word. Depending the nature of the vectorial function, in this case f. Any question, guys? Do you understand this or no? All right, opinion. Oh, it's coming more people. Jocelyn, understand. Victoria, Carlos Duque, David Restrepo, okay, Brandon Thomas, Robin, good. Omar Borja, Fiddi, and the student is coming early, no? It's Fiddi, Ricardo, Giraldo, and Annie Cruz. Okay, so you understand, no? It's easy, right? Let's do it one more. Curiosity. But in 3D, it's exactly the same. But in 3D, the only complication is that we have more dimension extra, no? Okay, suppose that you have vector field. It's giving, in this case, vector field is 2xy plus c cosine x, comma, x squared plus e to the z minus sine y, comma, y e to the z plus 3c squared plus sine x. Wow, too long vector field. Don't worry, be happy. Entonces, what is the first step? Compute the curve. Okay, let's do it. But the curve in 3D is different. The curve in 3D, remember, is equivalent to, say, nabla cross f. Like a cross product, because in 3D, the curve is a vector. So you put it here like the I, J, K. And 2D is easy, in 3D a little bit more complicated. And symbolic nabla, remember, is partial with respect to x, partial with respect to y, partial with respect to z. Yeah, I just copy here the expression PQR. P, Q, and R. 3 components. 3 dimensions. Entonces 2xy plus c cosine x, x squared plus e to the c minus sine y. Here we have y e raised to the c power plus 3 times c squared plus x. Okay, let's do it. Let's do it component by component. Okay. I. Remember, you delete mentally this and this. And you focus in this determinant. Okay, this determinant is I component, is partial derivative here with respect to the y. Because the only guy que depending on y is this. This is e to the c. E to the c. E to the c. E to the c positive. And here is e to the c because the derivative e to the c is e to the c but minus e to the c. Minus j, so you delete mentally this and this. And you focus see now in this. Let me see this and this partial derivative is partial derivative with respect the x of this expression. Que es, bueno, the only guy que depending on x is sine, derivative sine cosine. Minus partial derivative this with respect to z, this and this. Is, well, with respect to c. This is 0. The only c que we have is this, and the derivative c with respect to c is 1. I multiply by the coefficients in front of cosine x. Plus k. Plus k. You delete this mentally, this and this, and focus in that part. It's partial derivative with respect to the x and 2x. Nice. And partial derivative with respect to y. Y here only is 2x. Wow, minus 2x. This is obvious. Everything is 0. See, everything is 0. And the curve is a vector 0. You see in 3D is 0, 0, 0. It's a vector. Null vector. Entonces, we discovered que our famous vector field is conservative. And I need to find the potential function. I need to find the potential function. To find the potential function, you compute the anti-gradient. Step by step. You integrate p with respect to x. You integrate q with respect to y. And you integrate r with respect to z. Component by component. Who is p? Well, p in our example was, let me copy. 2x is antiderivative 2xy plus c cosine x dx. And you consider only the x is a variable, the rest is not variable. Entonces we have x squared. Why? Because it is power rule, increasing the exponent plus 1 is squared by 2. The 2 is cancelled out, and the derivative of the antiderivative, sorry, of the cosine is sine. Entonces plus c sine x plus something I don't care. Okay? Remember, because the shortcut is you take the collection of any expression to form my potential function. Okay, antiderivative q. Who is q? Q is x squared plus e to z minus sine y. And to say with respect to y in that case. Entonces x squared y again because this is a constant. Entonces plus. Okay, plus e to the z y. Minus because it's antiderivative, minus or plus. Antiderivative Sine es minus cosine, ¿no? You have a minus in the front, entonces positive. Plus cosine. Okay. Now antiderivative r. Who is r? R is y e to the c plus 3 c squared plus x dz. Entonces now you antiderivative with respect to z. Entonces y e to the z, because antiderivative e to the z is e to the z, plus this is c cubed, because increasing divided by 3, and this is c sine, so c multiplication by sine x. Okay, we finished. Now ready to set out the potential function. Okay, in this case, depending of the 3 variable is let me see. I can see this expression here and here. I take one time. I can see this expression here and here. I take one time. One more. Oh, look at that. I see this expression and this expression. I take one time. It will see y plus c cubed, no? Okay, stay alone. And cosine y. Wow, don't know. Let me see. Yes. Yes. Plus, no? X plus. Okay, this is the potential function. Now the potential function, I forgot to say the objective of this problem is compute the line integral from the point 0, 0, to the point 1, 1, 1. No specific curve f that the r, the trajectory is not important. So suppose que I am doing the sketch, okay, in 3D, x, y, z. We go from 0, 0 to 1, 1, I suppose que here, 1, 1. I travel for the totally arbitrary trajectory. And the word or the circulation integral is the same. And you evaluate, and the rest is you plugging in 1 and plugging in 0. When you plugging in, be careful, when you plugging in 0, okay, plugging in 0, 0, 0. Es obvio que this monomial is 0, sin 0 es 0, exponential es 0, tan 0 es 0, 0 cube es 0, pero cosine 0 es 1. And you evaluate in 1, 1, 1. Well, this is 1 plus 1 times sine 1 radian, I suppose, plus exponential 1 is e, plus 1 cubic is 1, plus cosine 1, something like that. Entonces es like a 2 plus e plus sine 1 cosine 1, no? So what is my final answer? My final answer is subtraction, f 1, 1, 1 minus f 0, 0, 0. Entonces es 2 plus e plus sine 1 plus cosine 1 minus 1. Entonces 2 minus 1 is 1, and the final answer is then. The final answer is then 1 plus e plus sine 1 plus cosine 1. Easy, super easy. Okay, do you understand the idea, guys? It's no big deal. It's super easy. Any question? Potential function. Proof. This is the step-by-step methodology. You compute the curve. See, the answer is 0 in 2D or in 3D 0 vector. Then I understand it's conservative field. Therefore, my goal is compute the potential function. The potential function is the anti-gradient, component by component. And after you evaluate in the start point and the end point and subtraction. Any question? No, it's easy. No, it's important, and I create the review package, but I don't want to say now. Also, we have a lot of problems, so we solve it in this way. It's easy. Okay, let's move on to the new topic. It's a green theorem. Well, green theorem is fantastic. It's fantastic because state the relationship between one line integral. So, for example, let me try to copy the formula of the green theorem and explain something about the hypothesis behind the green theorem. So, green theorem convert my line integral closed curve, always closed curve. See, it's open now. It's only for the closed curve. For example, of the one vector field, that dr. Okay, by the way, you know that we can write this line integral in that way: p dx plus q dy. You remember that this comes from when we are doing the dot product, fspq. By the way, green theorem is a 2-dimension only. In 3 dimensions, we see another theorem that is similar, pq, and dr. This is the vector field, no? And dr, by definition, is dx comma dy, no? You perform the dot product, your multiplication, this times this, and you get this idea. But this is not important. We saw before this. So the important is now. This is equal a double integral. Wow, a double integral. You change the line integral to another double integral and the region R. Okay, I want to explain who is the region R of the partial derivative Q with respect to X minus partial derivative P with respect to Y dA. And by the way, this guy is a curve in 2D of the vector field. Bang! And this is the green theorem. Okay, look. The supposition behind green theorem is, look, we have a closed curve, 2-dimension problem. We have closed curve. This is our C. Always the supposition is case counterclockwise. It's important, this supposition. Si es clockwise, bueno, es okay, pero es negative. So the green theorem is the same formula, but you need to introduce one artificial negative one. Entonces, this is called, when this situation happens, when it is counterclockwise, this is called positive orientation. Positive orientation. I want to explain it after orientation. Suppose que it's easy to understand the idea si es compatible or not the orientation. Suppose que one guy here walking on the curve, of course in the direction indicated by the curve, walking, and the left arm, always pointing to the region. Okay, this is the region, by the way. This is the region R. And the region R is the region bounded by the curve. Entonces es magic, guys, because you convert the line integral in one double integral. Entonces, bueno, okay, I understand, but what's the problem? One of the problem is que maybe it's easier compute the problem using the double integral, and maybe sometimes it's easier compute the problem using the line integral. So we have two possibilities, or line integral or double integral. And by the way, the answer is the same. Okay? This is the part. This is a part of the green theorem. Basically, is circulation. So line integral circulation. circulation. Okay. And we can compute it in the flux. Yes, we can compute it in the flux. The Green theorem contains two parts. The part of the circulation is this, okay, and the majority of the book only explain only circulation, and that's it, end the story. However, no, I want to explain another possibility to apply the Green theorem for the flux. Suppose we have the integral, the vector field, and one curve C, but in this case you have m ds. Remember, another way to express dr is dr vector is dx dy or tangent vector dot product ds, and this ds is exactly the same ds. Okay, this is the r length infinitesimal, okay, element, no, inside the curve ds. And the formula I proved in the last class, okay, the formula for the flux, this is the flux. The flux is similar to this. It's a little bit different. It's p dy in the curve C minus q dx. This is the formula to compute the flux. When you have the vector field, when you have the curve, parameterization maybe. But I want to see that there are certain analogy in Green theorem. So this is my flux. I want to compare with the circulation, because the circulation is integral from C p dx plus q dy. Oh, something is different, right? Let me organize in this way. I put minus q dx. I put here plus p dy. Okay, I organize in the way because I want dy is dy here and dx dx. And you can see okay, p, this p actually is in the formula like a minus q. And q in my formula is like a p. Q is like a p. Look, it's like a p. Okay. So using this analog idea, in order to compute, for example, the curve of f like a qx minus py, well, okay, when you compute the curve of f is, remember, q is p, this is px, minus p is q, this is minus q, y. And we have double minus, this is px plus, wow, qy. So in this case, this matching perfectly with the definition for divergence. A divergence, by definition, is partial derivative p with respect to x plus partial derivative q with respect to y. This is the definition. Okay, I take advantage of this. Then the Green theorem apply and the flux idea. Flux idea, remember, p dy minus q dx. Wow, it's equal double integral in the same region R, bounded by the curve, and the superposition is the same, it's called y. This is called a positive orientation. Now here, the operator that we have here is not the curve, it's divergence. Diverge f dA. Wow, it's a flux. It's a flux version of the Green theorem. It is a circulation version for the Green theorem. And the majority of book leave it like that. However, I like to write in this order. The double integral in the region R of the curve of f dA. Okay, circulation, Green theorem. Flux, integral, Green theorem. Okay? So, conclusion. It's no big deal. It's no big deal. The idea is clear. The idea is you have a formula, and this formula allows convert the problem in two different point of view. Or you are doing using the line integral, or you are using this double integral. Entonces, suppose. In one problem, que we have different, for suppose que the one curve, well, this is a Helix, something like that, but no, in another problem, the curve is formed by different segments. For example, one curve is multi-segment or multi-pieces, like that. If you want to compute the line integral and this compound closed figure, you need to find the curve C1, the curve C2, the curve C3, the curve C4, the curve C5. To say my problem is not one problem, it's 5 problems of the line integral. However, see you see that this is a closed curve, and you find the double integral in this region R, it's easy because you're using only one. But you see in another problem is completely backward. So I prefer the line integral, not the double integral. Let's see example to understand this. I bring the first example. Do you understand the idea of the Green theorem? Okay, let me repetition again. Green theorem is a formula que está in relationship between line integral and double integral. Entonces, change a little bit the expression, no? See, the line integral is circulation, we're using curve. The line integral is flux, line integral. Entonces, now my integrand function inside the double integral diverges. And remember, make it sense, because flux somehow is related with the source or sink, no? However, divergent give me information about source or sink. Entonces, this is at least physically matching perfectly. Any question, guys? Let's do an example of the green. Green is important. We see in the review packet some problem about the green theorem. Okay, suppose example 1, green theorem. Compute this. So it's important to understand the green theorem only is valid for the closed curve. See, it's open, no. This is the, so basically we have computed this integral, okay. Entonces I need the specification. What is our curve? Our curve is a triangle like that, look. We have the point here 0,0. In this direction, we go to the 1,0. This direction, so the orientation is important. Here I go to the point 0,1 on the y-axis. Okay, like that. And finally, closed curve, like that. This is my curve C. This is my C. What about the vector field? I am confused. I don't understand, Professor, very well. What about the vector field, I suppose? Que es PQ, no? PQ. And who is PQ? This is P, and this is Q. And my vector field is then x to the 4 power, comma, x1. If you want to understand, but no, not necessary. Entonces now es obvio que in this example, it's easier compute the line integral, this line integral, using double integral. Because you compute the double integral, the line integral, sorry, you need to separate this in 3. So this is line integral in the closed curve C is equal line integral in C1 plus line integral C2 plus line integral in C3. This is C1, this is C2, and this is C3. And this is no big deal, but it's too long process, no? Entonces, much better, let's do it using green theorem, no? In green theorem, I need to change the problem in another problem, que es double integral in the region R, que by the way, the region R is this region, que I highlight in yellow color, no? Of the curve of the vector field dA. I put dA, not dx dy, or dy dx, because I don't know if I feel it in polar or in rectangular. No? I suppose que rectangular, because no, my region do not involve circle or semicircle or quarter circle. Entonces no polar, it's xy maybe. Okay, entonces first of all, I compute the curve. By the way, guys, if the curve is 0, wow, entonces this answer is 0, and this is because the vector field is conservative, ¿no? Entonces any line integral doing in one closed curve and one conservative field is 0. Pero no, in this case no. In this case no is 0. I create intentionally, no. Entonces the problem in 2 dimensions, because green theorem is 2 dimensions, is qx minus py. It's the formula for the curve in 2 dimensions. Then this is p, and this is q. Entonces you differentiate q with respect to x, y. Minus, and you differentiate p with respect to y is 0. The answer is y. No 0. No 0. Entonces this vector field is not conservative, no? Entonces now I change my problem, and this problem is the double integral, the integrand function is y. Now it's a moment to define in what direction I want to perform the integral. I suppose the double integral I do in that direction first, and after I extending in x direction. So I perform the line integral, so dy first, dx secondly. Yeah, I go from the y0 here, y0 to the y of this line. The y of this line is 1 minus x, no? Because the equation for this line is x plus y equals 1, no? You solve for y, is for the 1 minus x. Okay, now finally, extending from 0 to 1. Boom! We compute this double integral. I want to skip the step because it's too easy for us. Okay, and this is just arithmetic. And basic cal 1, and the answer is 1 over 6. End the story. Green theorem, fantastic. Allow all conversion. Line integral, in this case, the closed curve is formed by 3 pieces. Those are too tedious doing it that way. However, it's easier conversion to the double integral. Do you understand this or no? Okay, opinion. Clear or confusing? Marco, it's okay? Answer me. Yes, no. Jocelyn, que you are smart. Always. Okay, he said yes. What is the interpretation? Interpretation. Okay, you want to know every interpretation. No interpretation, it's just mathematics. So they are connection. It's a formula, state connection in between double integral and line integral. No connect, no interpretation. No interpretation. No interpretation. Well, okay. Always we can find interpretation. It's like it's no area. No. It's no area. It's, okay. Let me try to find some interpretation. Some book try to make interpretation. Look, suppose this triangle, no, okay, our region. No? Our region is a triangle. Now, no area because the integrand function is a curve, is y. Entonces, the interpretation of the curve, remember, curve is like a local property, no? In every point, bam, 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 we have a curve. And the curve give me information in what direction rotate, no? So we have infinity microscopic curve. Well, okay, professor, but it's too long. No, because I using integral, double integral, so double integral. So we are doing, okay. We are doing, okay, in the green theorem, look, we convert this to double integral, the curve of f dA. No? So you can interpret it like a summation. So you are doing something. Remember, integration is Riemann sum. Then you are summation any curve, summation any microscopic curve. I suppose can the middle of the triangle cancel out some component because in this case go in one direction, in this case go in another direction. However, it's unbelievable that the summation in double integral give me the information of the line integral que is like a curve, a big curve in the boundary. Okay, this is the region R. The summation any microscopic curve give me the big curve, que is the line integral. In the boundary. By the way, I want to introduce a new notation. This is C, and C is the boundary is R. And boundary in calculus called a boundary, this delta again, like a partial derivative, but actually it's not partial derivative. This is boundary. Boundary. I don't know, Gerardo. See this interpretation of the summation, every microscopic curve, give me the total line integral in the boundary. Because in the middle, I don't care. In the middle, cancel out some component, partial component, and stay alive only the component in this direction, or in this direction, or in this direction. This is the interpretation, but it's not clear. The proof of this theorem is very complicated. It's totally beyond to the scope of this course. You use it, and that's it. Gerardo, a little bit. Okay. I try to do my best, you know. Okay. Well, let's see what another example 2, but totally backward. And the example 2, we are doing in the opposite direction. So in this case, much better. Apply the line integral, no the double integral. Okay, entonces, for example, this applies specifically when you compute area. Let me try to explain the theoretical part behind this, and after I go directly to the example 2. So suppose I copied my green theorem. My green theorem must say the integral closed curve of the P dx plus Q dy is equal double integral in the region R, and remember C is the boundary of R, and I suppose the hypothesis is counterclockwise direction, is positive orientation, is called it like that. And inside here you have the curve, okay? The curve is Qx minus Py dA. Suppose I want to compute area. Well, this is a fantastic way to compute area is using double integral, but the integrand function should be 1, no? So I enforce the situation. Okay, the integrand function is 1. Well, entonces now we're using, let's see. So suppose it's 1, there are many possibilities to suppose that this is 1. The most common supposition is suppose that Qx is 1/2 and Qy is negative 1/2, because positive 1/2 minus 1/2 is 1. Okay. And you say, Professor, that there are other combinations. Yes, there are other combinations. However, the most frequently combination is using is this. After this supposition, I want to derive formula. Entonces, under this supposition, Q is equal 1/2 x, because you compute the antiderivative of this. And likewise, P is minus 1/2 y. Okay, pero entonces I come back no to the double integral, sino to the line integral. So in the line integral, I compute the line integral in the closed curve, and PQ, so the formula is minus 1/2 y dx, because P is this, plus 1/2 x dy. Entonces you factor out 1/2 outside the formula, the integral, and organize a more elegant way, que is x dy minus y dx. Wow! And we can use in this new formula to compute area of the closed curve, of course. So it's another application of the green theorem, but in opposite direction. I need to compute the area, and why not? You, instead of doing by double integral, because maybe it's hard, or I don't know, you see that in the example. Suppose the example I bring now is relatively easy. Example 2 is you need to find the area. Area of what? Of the helix. Find the area of helix. Helix like that. X squared over a squared plus y squared over b squared equal 1. There are many ways to do this. Many ways. But okay, let's do it in the new formula. Okay, we have in our hand is this formula, no? Okay. See, I make a decision to do by line integral. So the first thing you should do is parameterization. This curve. This is a curve, right? This is the closed curve. Everyone know very well helix. Helix look like that. Suppose que, bueno, okay, A is associated with the X. This is the major axis. It's A minus A. And it's a B and minus B. X and Y. I suppose that the curve is counterclockwise. And let's do in the parameterization. The parameterization is easy as always. You suppose that X over A squared plus y over b squared equal 1. And you suppose the famous trigonometric identity function is a cosine t squared plus sine t squared, no? Equal 1. Therefore, x is equal a cosine t, and y is equal b sine t. And don't forget, please, when you parameterization something, a specification of the domain of t. Because basically, when you are doing parameterization, the thing we are doing is like a chain of variable. You substitution something, no? X, y, get the original variable by the new variable, get t. But the advantage is that t is only 1, and t is in between, in this case, 0 to pi. I did the parameterization of this. Okay. Now, I need to compute the area. And the area is the closed integral in the curve C, okay, this is the curve C in parameterization form, of the multiplication x dy minus y dx. So I need more. I need not only x and y, I need dx and dy. But this is easy. This is easy because you differentiate calculus. Dx is the derivative of this. Derivative cosine es minus sine. Entonces, let me erase that part. No good. this is dx is equal a minus a, no? Minus a sine t dt. Don't forget dt. And this is sine t, the dy is derivative sine cosine, b cosine, cosine t dt. Okay, put everything together. Everything together. You convert this line integral and one regular integral, like a calculus 1, under the idea for the parameterization. Parameterization is magic because allow us to compute line integral to regular integral. The limit is from 0 to pi. Now x, who is x? This is x, a cosine t. Multiplication by something, dy. Who is dy? Is b cosine t again, dt. Okay, you want to put it in the end of the integral. Minus y. Who is y? Well, y is b sine t. And dx is minus a sine t. Well, all will happen. This is ab cosine square t. This is plus because we have double mind ab again sine square t dt, and the common factor ab out, and we have cosine square t plus sine square t is 1. AB is a constant, you know. Integral the constant is ABT. And T evaluating between 0 and 2 pi. The answer is 2 pi AB. 2 pi no. 2 pi. Wait. Let me see. I forgot something important. I forgot in the equation. Look. The equation is 1/2 here. I forgot to copy 1/2. I underestimate this element. Entonces divided by 2, 1/2 here, divided by 2 is PAB. I remember que es PAB. PAB, and this obeys perfectly to the formula for the Helix. Try to find using geometry or another way. Suppose one particular case of the Helix is a circle, and you know very well by memory in high school that the area of the circle is pi r squared. And the reason that r squared is because A and B is the same. Entonces R, si A is R and B is R, entonces es R squared. Super. Do you see application or no? To find the area, it's another possibility. Okay, guys. Let's move on to another more complicated example. Because the green theorem. O sea, do you follow me? Everyone follow me? It's crazy, it's important, it's clear, it's confusing. Follow. Okay. Good. Duque, you see I posted your grade in the Blackboard, right? For the test. Something, I don't remember, it's 2 or 3. Yeah, okay. Pretty clear. Okay. Let me try to explain another possibility. Okay, give me the green theorem. Well, okay. We are talking about a simply connecting curve. Okay, what is that? Simply connecting curve. Simple connecting curve. It's the curve like that. Bam, that's it. But sometimes we have non-simple connecting curve. Non-simple. So when it's not simple, when you have, for example, some hole, and we can apply the green theorem. Yes, we can apply. How? Well, because you consider, for example, to understand that you apply, but in this case, you apply under the consideration that the outer curve is counterclockwise like that, but the inner is clockwise. And the region is this region. Okay, you have two curves. One region. The region is when you apply double integral. And the double integral is applied here. However, we have C1 and C2. Okay, and we apply this. What is the idea? One of the idea is suppose that I break it down this non-simply connected curve and two curves. Suppose that I travel in this direction. However, in one arbitrary point, I change the direction inside. Okay, you travel now here clockwise. You travel now in opposite direction, and exactly in the same segment. We continue travel here in one specific point. You point here. Okay. Again, you travel in the same direction, and you come back here. This is so obvious that we have this problem. I separate two problems like that. Okay, and another problem like that. Okay, now the idea is this direction, this direction, this direction, this direction. And why no? And why no? This problem is in this direction. This direction, this direction, and this direction. And we put together this part. It's obvious that this part is cancelled out. So this piece of the line integral is equal to this with the opposite sign, because the same member of the change the direction. And stay alive only two integral C1 is outer counterclockwise and C2 is the inner clockwise. Do you see? It doesn't matter if you have different hole inside, and the hole inside you treat like a clockwise direction, and the outermost is counterclockwise. I bring example. To illustrate very well this idea. Easy. No big deal. Okay, look. Example 3. This is example 3 of the green theorem. In example 3 of the green theorem, we have, for example, this line integral and the close. No simple connecting. Okay, it's 3x minus 2y dx plus x minus 4y dy. And the C is that curve, que es non-simply connected. Bueno, ese circle, radius 1, and we have another circle, radius 4. And of course, the rotation is counterclockwise here and clockwise here. And our region in which you apply the green theorem is this. Okay, actually, my curve C is compound, so not simple. C is C1 and C2 together. And we can compute this separately. Yeah, we can compute it separately. No, but no. The best way is not compute two, compute only one double integral in the region R. So to compute the integral in the region R, you need to understand first what is the vector field associated with this integral. So the vector field associated with this integral is PQ. This is P. It's a Q. Okay, it's a 3x minus 2y, comma, x minus 4y. This is my vector field. Entonces now I know, according to the Green theorem, que is a double integral in the region R of the curve of this vector field dA. I put dA because I don't know si ending in polar, or I suppose que ending in polar because it's a circle, right? No xy anymore. No. So I compute the curve. The curve in 2D is easy, is qx minus py. Let's doing. You find the derivative of this q with respect to the x. So q is x minus 4. Why? Therefore, qx partial derivative is 1. Wow, derivative x with respect to x is 1. And derivative for y is 0 with respect to x. And likewise, p, this is p. P is 3x minus 2y, and you differentiate with respect to y. Es obvio que es negative 2, ¿no? And the formula, entonces we have 1 minus 2. Es 3. Wow, it's easy. It's easy when the integral function is a constant, you know, it's super easy. Entonces, basically, I copy this again, but I copy R and copy 3 dA. Wow. So I make a decision, polar, no? Polar coordinate. Polar coordinate. So I change this region R in polar. The integral function is 3. Entonces this is R dr dθ. R go from 1 to 4. Look at that. Radio, go. Okay, radio is measured from the origin, from 1 to 4. And it's obvious that theta go from 0 to pi, because both circles are completely full circle. And you compute that. Easy. You can separate if you want into integral, no? You put it 3 as a constant, the theta part alone, the theta. At least I know that the answer of this is 2 pi. 2 pi times 3 is 6 pi. And the integral from 1 to 4 of the R dr. Okay, R dr is R squared divided by 2, no? Evaluating between 1 and 4. Entonces es 16 over 2, que es A, no? 16 is A minus something. 1 here, 1/2, no? 1/2. 1/2. Okay, now we have 2. We have 16 minus 1, 15. 15 over 2, no? Okay, entonces, what is the answer? Well, the answer is 3 multiplied by 2 pi multiplied by 15 over 2. At least these two cancel out. 45 pi is the answer. Okay, guys, I promise. Okay, we study line integral. Line integral is always complicated, very complicated, because the problem is that you need to parameterization something, you know. However, see, our line integral is performed in the closed curve, and we can apply Green theorem. Okay, not always we can apply. I forgot to say, okay, one more hypothesis for the Green theorem is, okay, the function must be continuous inside the region. If the function is continuous inside the region, it's okay. If the region is discontinuous, for example, normally some function is discontinuous in the origin because division by 0 is undefined, so we cannot apply Green theorem. So there is 2 conditions to apply Green theorem. Number 1, closed curve. So inside the region, the function PQ, both are continuous. Otherwise, no. Okay. Entonces it's easy, right? No problem, guys. Wow. Green theorem. And we study 2 more theorems, but not now, in the last moment. So what is the thing that we need to cover? We almost finish. Almost. I promise you we have a lot of work so far. Next topic, okay, maybe we start today, es the surface integral. Wow, wow, how many integral we study? Bueno, we study in Cal 1 the regular integral, pero en Cal 3 we study double integral, we study triple integral, we study line integral, not necessarily close, line integral, sí. And we study after that, I promise it's the last one, surface integral. Surface. Okay, line integral, new, Cal 3. And surface integral. Of course, I discussing in detail interpretation of this new integral, and this is the last one. And after that, I study connection in between this integral using theorem. Well, the first theorem that we studied today was the green, and the green state the connection between the line integral and double integral. But I promise you see another more interesting connection. Okay, I try, when the course is over, I try to understand the big picture about integral. Okay, let's move on to example 4, no? Example 4 of the green theorem. Es the integral in the closed curve of the y squared dx plus x squared dy. And who is z? Let's see, is the uni square. Uni square. Like that. This corner is 0,0. This corner is 1,0. This corner is 1,1. And this corner is 0,1. And of course, we travel control go y. Entonces, suppose que in one problem can never happen. So 99% you consider control go y, rotation, ¿no? Que es the positive orientation. This is synonymous to say positive orientation. Si es, you know, que si es clockwise, entonces es, you can apply, yeah, you can apply the green theorem, pero you know que es minus, and that's it. That's it. Okay. Okay, this is the problem. Okay, what should I do? Parameterization, these three segments, and compute the line integral in C1, in C2, in C3, and C4. No, it's crazy. You take advantage, green theorem, and compute the double integral in the square, okay, super easy. Okay, so first of all, I need to identification my vector field. My vector field is, remember, PQ. PQ. Remember, green theorem is only for 2 dimensions. When you have 3 dimensions, PQR is another theorem, no green. Entonces now I compare with my idea I have in my brain about this is PDX and this is QDY. Entonces it's obvious que in our specific problem, P is y squared and Q is x squared. Okay. Now I compute the curve because I know que in green theorem you convert line integral to double integral. This double integral in the region R. Okay, by the way, the region R is this region. The integral function is a curve of the vector field dA. You ending maybe in Cartesian or polar. I suppose that this is Cartesian, it's obvious, right? Entonces we compute the curve. The curve is the formula. It's Qx minus Py. Partial derivative Q with respect to X. This is P, this is Q. Es 2x, no? 2x. Minus partial derivative P with respect to 2y. Okay, this is my curve. So basically, my double integral look like that. 2x minus 2y dA. Okay. Okay, this is a moment to set up the double integral. The integrand function is 2x minus 2y. Suppose que integrate, remember, si there are no options, si hay no restrictions, something complicated, I prefer this order of the integration. So your integration dy first, dx secondly, ¿no? Ajá, entonces now del límite es obvio que es from 0 to 1, 0 to 1, boom, easy. I did that. The answer is 0. Wow, it's 0. It's 0, however, is no conservative vector field. Because you determine that the curve is not 0. Okay, the idea is all conservative field, the gradient is 0. However, not all non-conservative, the integral is 0. So there are another case non-conservative, however, the integral in the closed curve is 0. Okay, so the converse idea is not true 100%. The idea is true 100% if the vector field is conservative, for sure, the integral in one closed trajectory is 0. Super. Any question in this elementary problem? I have another more. I take advantage to introduce the next topic. Okay, another example, easy, similar. Easy, pretty easy, Ricardo. Okay, I love you, the theorem. The theorem is easy. Example 5, no? Es, suppose the integral close 3xy dx plus 2xy dy. And who is C? C is a rectangle like that. From -2 to +4, 1, 2, 3, 4, to 2, to 1, to 1, to 1. Okay, es a rectangular like that. To 2. Okay, control y, of course. This distance is 1, and this distance is 2. From -2 to +4. This is my cursor. It's a closed curve. Super. Now, identification. Identification, the vector field. The vector field is PQ. And our specific problem is 3xy and 2xy. To find the curve, the formula is qx minus py. Do you see that I copy always the formula, no? Because my intention is that you somehow memorize this. It's super easy. When you differentiate derivative q, okay, this is q, and this is p, derivative q with respect to x is 2y, it's obvious que 2y, minus derivative p with respect to y is 3x. Okay, 3x. This is our curve. It's a function, scalar function. In 2D es scalar, in 3D no, but in 2D es scalar. Then I set up my double integral because I make a decision to apply green theorem in this region. This is my region in the green theorem. Look at that. R. This is my double integral in the region R of this integrand function is the curve dA. So now this is a crucial moment in which I make a decision si es Cartesian o es polar. It's obvio que es Cartesian because it's rectangular, ¿no? Entonces I copy 2y minus 3x. Entonces I prefer always integration in this direction. And extending in this direction. Entonces now the dy part go from 1 to 2. And the dx part go from -2 to +4. The rest is integration, calculus 1, iterate integral, you integrate this part first, evaluate, and integrate the second part. Second, the answer again is 0, and this is the confirmation, it's a coincidence in this problem, that not always the integral in the closed curve is 0, is because it's conservative. Bauer, yes. Si es conservative, I guarantee 100% que the integral de closed curve is 0. But in opposite direction, the converse direction. No. No. Okay. Okay. In the 10 minutes that we have, I want to introduce next topic. Any question, guys? No? Okay. 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 Let me erase the board. Okay. Now we study new topic. It's a little bit complicated. It's parametric surface. Parametric surface. Okay. Are you familiar with the parametric curve? Okay, we studied long time ago, and we apply here in la integral. But we need to parameterization now surface, because we need to apply in the surface integral, que is the next topic que we discuss in this week. Entonces, let me recall one thing that you very well know. Recall parametrization curve. Parametrization or parametric curve. You define a vector value function like that. Normally, the name of the parameter that we use is t, or not necessarily always is t, no? Maybe t, maybe theta, maybe x. This is the vector value function. So this t is the ordinary number in general, or not necessarily ordinary number, specification interval. But we, in the output, we have three components, x, t, y, t, three functions, que represent vector value function, ese vector. And t, very important, don't forget that part, vary from A to B. So when you are doing this, look, when you are doing this, actually, the thing that we are doing is, we have all real number here, this line. We have one subset here, is a specific interval, A to B. And you stay a connection with the three-dimensional context. This is x, y, z. And in three dimensions, we have a curve. Okay. And for example, this point, okay, I want to call P1, and this point I want to call P2. Well, this point P1 is the R evaluated in A. It's like a vector. And this is like a position vector, no? So the position vector is come from the 0 to the specific point, and the P2 is the R evaluated in B. Okay, it's the same A and B that we have here in the real number. Basically, the thing we are doing fantastic is a one-dimension problem. You convert in three-dimension problem. However, it's three-dimension ambiental. However, my object is one dimension because it's a curve. It's obvious that the curve is one dimension object because we have no width, we have no height, we have only length. Okay, by the way, if you want to compute, it's the R length. I suppose that you understand very well because we practiced several times parameterization curve, parameterization curve, parameterization curve. Okay, the problem that we are doing now is parameterization surface. Okay, parametric surface. This is new. Parametric surface. Okay, and surface is different because surface is, okay, a curve A curve is one-dimension object que may be living independent de ambiental 3D or 2D. This is ambiental dimension, and this is the dimension for the object. Surface, no. Surface 2-dimension. The classical surface que we study cylinder, we study ellipsoid, we study paraboloid, a surface. When you talk about surface, it's not solid. It's, hollow. It's only the outer part of the surface. Entonces, the surface is the 2D dimension, of course, because we have maybe a length and width, no height, because you suppose that the thickness of this surface is negligible. However, we have two-dimension living and 3-dimension ambiental, something like that. Look, suppose that we have 3-dimension ambiental. One more time, we have surface like that. Oh, no good. Like that. I put this line to indicate that somehow this is 3-dimension, no? So not necessarily flat, not necessarily like a double integral que es totally flat. No, this is the curvy, little bit curvy. Okay? Now you define again one famous vector value function. Look like a. Are you hungry, Ricardo? Yeah, in the grill, yeah. Okay, steak. Entonces now, suppose que you define, look, the new thing. Pay attention now. You define the vector value function similar to this. But in this case, we have two new variables, u and b. I promise that throughout the chapter, I change the name of this variable, not always UB. And it's similar to the not only T in the parametric curve. In the parametric surface, R is UB, or you can change, depending on the geometry. Maybe you feel more comfortable, call R theta, or another. So basically, it's the vector value function in which you have a function of X, look, X, Y, Z, but depending UB. And Y depending UB again, and C depending of UB. And that's it. No, of course, no. This is just the beginning. Look at that. Now, the domain of the U and B is completely different to this, case 1D. No. Now, in this case, we have 2-dimension. Look at that. 2-dimension. Suppose UB. And suppose that our domain of the U and B is represent like that. Okay, this is UB. Okay, this is UB. This is the domain. Look, this is the domain of the UB. And you associate any point inside here with any point inside the surface. But this is flat. And this is not flat. To compute integral surface, what is the range? The range, yeah, important. Is, for example, U vary from A to B, and B vary from C to D. This is important. It's important. You define the expression one by one, bang, and you specification the domain. And this domain is 2-dimension instead of here it is 1-dimension. Okay, 2-dimension and 3-dimension. What is the only difference? Okay, the only difference is this 2-dimension and UB is flat, and this 2-dimension and 3D ambiental is not flat, it's curvy. Entonces, in order to find the surface integral, you using this transformation, you transform it from surface integral, okay, I want to explain next class, to the double integral, because this surface is totally flat. This is super interesting, super. Guys, don't be absent. This week is important, super important, surface integral. Okay, guys, I stop recording.